Alright, so this is going to be a walkthrough of the questions and answers for the Unit 1 practice quiz. Just keep in mind that if you wrote down any of the measurements from this first section slightly differently than I do, that will alter your answers, so your answers won't quite match. But it's important to focus on how did I solve the problem, how did I set up the calculation, and did your setup match mine? And then if there's any differences due to rounding or a slight difference in the way we recorded the measurement, take that into account. The most important thing is that you come out of this understanding how to answer the questions. Okay, so in this first section, we're taking some measurements, and the first one is looking at a graduated cylinder. Now, graduated cylinders measure liquids in milliliters, so that's one thing you want to keep in mind is what is the unit that I'm using. It's milliliters in this case. The next thing you have to look at is what are the units on my graduated cylinder. This particular one has markings every 1 milliliter. You can see there's between the 10 and the 20 there's 9 markings, so that's a total of 10. So that means I'm going to record my measurement. If I have markings at the 1 milliliter mark, I'm going to record measurements to the 10th of the milliliter, and I'm going to estimate that last decimal place. And you always want to record one place to the right of the smallest marking on your container, whether it's a 100 milliliter beaker and you record to the tens, or if it's a 10 milliliter beaker you record to the ones. In this case it's a 1 milliliter marking graduated cylinder, so you record to the tenths and you estimate the last digit. Now in this particular case, it looks to me like this water is sitting exactly on the 20. So I'm going to record it as 20, but I'm going to record it as 20.0 milliliters. Again, you have to include that decimal point, that decimal place, even if you think it's a 0. Because I'm estimating it's right on the 20. Maybe you looked at that and said, I think I see a little bit just above the 20, so it might be 20.1. Maybe you think you see a little daylight under the marking, you think it's 19.9. So that plus or minus in the tenths place is where we might disagree, but we should all agree within 1 milliliter. It's, definitely more than 19, definitely less than 21. It's kind of right on the 20, so you might go a little bit either way, but you have to record that decimal place even if you think it's a 0. Now this is using a digital balance, so the estimating is essentially done for you. You don't need to do any rounding or anything. You just record the measurement as it appears. So here's the measurement here. I'm going to record that as 14.95, and the unit here for mass is going to be grams. Okay, so again, the balance is doing the rounding for you, so you just write down what appears on the balance. We do need to keep in mind the number of figures when we're doing calculations and rounding later, but you don't need to estimate anything here. So the final measurement that we're going to take is the volume of the cylinder after adding the piece of metal that was on the balance. That's our sample. So again, I'm looking at this, and the volume of the liquid is up here. Okay, the markings are still at the 1, so I still have to estimate to the tenths. Now it's pretty close to the 20, but I think I see a little bit of green above the mark, so I'm going to record this as 22.1 milliliters. And again, if you wrote down 22.0 or just 22, the calculations you do from here on out are going to be slightly different from mine, but just keep that in mind, that you might have a slightly different answer. But the setup is the most important part. So if we take a look at the readings that we got, right, we had the water in the first measurement, and then we had the water plus the metal. So if we want to find out how much the metal volume is, well, we have to take the water plus the metal and subtract the amount that we know is water. So when we had the water plus the metal, I wrote down 22.1 milliliters. Again, you might have written 22 or something like that. We probably all had the same answer for the first one, which is that the water by itself is 20 milliliters. So to find the metal, we take the difference between those two, because that's what caused the water to rise from 20 to 22. So the volume of the metal by itself would be 2.1 milliliters. Okay, so just taking the total, subtracting the part that was the water, that gives us the amount of the volume that's the metal. Okay, so now we have figured out the volume of the metal, which we calculated in the last question. We said it was 2.1 milliliters. In the first couple of measurements, we determined that the mass of the sample was 14.95 grams. Well, the formula for density is density equals mass divided by volume. So I've got the mass, I've got the volume, now all I have to do is divide. And when I do 14.95 divided by 2.1, I get 7.12 grams per milliliter. Both units stay there because nothing cancels out, and this is the unit for density, grams per milliliter. Now, I get 7.12, but the rules for significant figures say I can't have more digits than the smallest number of digits that I started with, which happens to be 2.1 in this case. So I'm going to round my final answer to 7.1 grams per milliliter. So that's the density of the sample. The next question is using some of the values we've calculated so far to figure out what is the thickness. Now we did this with the aluminum foil, so we're going to do essentially the same thing here. All right? Keep in mind that the volume is length times width times height, and that the area is length times width. So that means that the volume is really the area times the height. And then finally, that means that the volume divided by the area equals the height. Okay, so we have the volume. We figured that out in one of the earlier questions as 2.1 milliliters. And I'm going to take advantage of the fact that 2.1 milliliters is equal to 2.1 cubic centimeters, because cubic centimeters and milliliters are the same unit, okay, interchangeable. So I have 2.1 cubic centimeters. That's the volume. So looking down here, volume over area equals height. Well, I have the volume. The area is given to me here in the question. So I'm going to take that big number, 143,884,892 square centimeters. So now I have cubic centimeters in my numerator. I have square centimeters in the denominator. That means 2 of the 3 centimeters in my cubic centimeters cancel it out. So I'm left with the unit that is centimeters. Now when you do this in your calculator, 2.1 divided by 143,884,892, you get 0.00000014595 centimeters. Or if you're using another calculator that doesn't give you all those decimal places, it might give you 1.4595 e negative 8. Okay, that e is not for error, it's for exponent. It's a scientific notation note, right? It's the calculator saying, hey, I can't do the exponents, like the little superscripts, but I'm telling you this is times 10 to the negative 8th. So when you see that e, in your mind, I want you to picture times 10. And then the number that comes after it is the exponent that goes above the 10. So in this case, it's 1.4595 times 10 to the negative 8th, and that would be centimeters, But again, I have to look at the rounding. The unit I have for volume, or the measurement for volume, only has 2 digits. So at the end of the day, after all this work and all these zeros and all the scientific notation, I'm going to write this down as 1.5 times 10 to the negative 8th centimeters. And just to quickly go back and look at the scientific notation, the reason it's negative 8 is because if I'm looking at the decimal, the expanded version of the number, in order to make it scientific notation, I can only have one digit, and it has to be not a zero, one non-zero digit to the left of the decimal point. Well, this decimal point is way over here. So to get it so that I have one digit to the left, I have to move 1, 2, 3, 4, 5, 6, 7, 8 times to get to 1.4. Since I'm moving to the right and I'm turning a decimal into scientific notation, I use negative 8 as my exponent. That's why it's negative and not positive. Okay, so that's just a quick recap on scientific notation. So the final answer here is this 1.5 times 10 to the negative 8th centimeters. That's the thickness of that zinc atom. All right, so again, we have the grams from the balance that we looked at in the second question there, which was 14.95 grams. That's how many grams of zinc I have. In order to figure out the number of moles, I take the mass that I have, which is the 14.95, and I divide it by the molar mass. Well, the molar mass comes from the periodic table. And according to the periodic table, zinc has a molar mass of 65.38 grams per mole. When I divide that out, I get 0.22866, and it goes on and on and on. But the two numbers that I started with both have 4 digits. So my answer can't have more than 4 digits, which means I'm going to round this to 0.2287, and the unit here is moles. That's what we're trying to find. The abbreviation is MOL. Okay, so I took the grams divided by the molar mass. The molar mass comes from the periodic table. The grams comes from our measurements in the first part of the quiz. And then I rounded to 4 digits because the numbers I'm working with each have 4 digits. Now that we know how many moles we have, we can use that to figure out how many actual atoms there are in this sample. And we do that by taking the number of moles times this number, which is called Avogadro's number. It's the number of particles in 1 mole of anything. So the number of moles times the number of things in 1 mole is going to give us the number of things. Just like if you want to know how many eggs are in 3 dozen, well, you know 1 dozen is 12, so you multiply 3 times 12, you get 36. That's how many are in 3 dozen. It's just that this number here is a little bit weird, but the process is the same. So in this case, I'm going to take the 0.2287 moles that we had in the last question times 6.02 times 10 to the 23rd atoms per mole. And when I do that, I get 1.37677 times 10 to the 23rd. All right, well, again, rounding-wise, the number of atoms in a mole is a constant value. It doesn't factor into rounding at all. It would just be like counting. You're not estimating. There's no rounding necessary. This is how many things there are in a mole, just like there are 12 things in a dozen. That's just a fact. So the number I have to look at is this one. And since this number has 4 digits, I'm going to round my final answer to 1.377 atoms. Okay, because we're counting the number of atoms we have. Oh, sorry, times 10 to the 23rd. That was almost a big mistake. Because it's not 1 atom. It's that many atoms with another 20 zeros after it. Atoms is the unit. Okay? So take the number of moles times the number of things in 1 mole, which is this Avogadro's number. That gives you the number of atoms in your sample. All right, and then the last question. how much would it cost to ship this little tiny piece of metal into space at the estimated rate of about $2,000 per pound to send cargo into space? Well, we know how many grams the sample is. It's 14.95 grams. But we want our answer to be in dollars, so I'm going to have to convert my grams into dollars somehow. Well, I'm given the cost, but I'm given the cost per pound. My answer, or my measurement isn't in pounds, it's in grams. So I'm going to have to convert the grams into pounds, and then I can use the cost per pound to figure out how much it will cost. So I need the two conversion factors here. The first one is given to me as 1 pound is 454 grams. Since I want to get rid of the grams, I'm going to put that down here on the bottom, 454 grams, that's 1 pound. And then, now that I will be able to cancel out the unit of grams, I've got pounds. So now that I have the measurement in pounds, I can use the price per pound to figure out the cost. So the next conversion factor, I need to put pounds on the bottom, and the cost per pound on the top, which is $2,092 per pound. The pounds cancel each other out, and so the only unit left is the dollars, which is what I want. So again, before I've done any calculating, I can be pretty sure that this is set up right, because all the units I don't want are canceled out. The unit that I want for my answer is left. So now I can multiply 14.95 times 2,092, and then finally I'll divide that answer by 454. When I do that, I get $68.8885. But my starting measurement has 4 digits, so I'm going to round this off at 4 digits. So my final answer will be $68.89 to send that little piece of zinc into space at current rough cost. So that's the last question. Those are the types of questions that will be on the quiz, just like that. Obviously, there'll be some slight differences. The measurements will be a little different. The exact questions that I'm asking might be a little bit different. But those are the questions, those are the things you need to study for the actual quiz. That's how you solve these problems. Anything like conversion factors that you need, other than things like minutes and seconds, I'm going to assume you know that. Things like pounds and grams or miles and kilometers, anything like that that you need, I will give you. You may and should use a calculator, and if you need any information from the periodic table, I will give it to you. Or I'll give you either the image from the periodic table or just give you a periodic table to refer to. And so that's going to be it. So good luck, and we're going to get on to actually taking the quiz.